we are going through the rotational motion. In the last part, we have seen about the centripetal force, centrifugal force. Also for the uniform circular motion, non-uniform circular motion. Uniform circular motion with, that is the circular motion with the constant linear speed with constant angular speed, whereas in the non-uniform circular motion, here the speed is not constant. The formula is important, that is F is equal to mv square upon r, or that is equal to mr omega square. Now the next part of the chapter, the motion of the vehicle along the circular track or the curve, that is at the turn the vehicle performs the circular motion. I have told you that for every circular motion there is a need of the centripetal force, that is mv square upon r or mr omega square, which get balanced by the centrifugal force. Both are having the same formula. Now along the circular track, the vehicle perform the part of the circular motion. For the circular motion, there is a need of the centripetal force. Now in this, we are going through the different derivations. That is number one, the most safe speed along a horizontal circular road. Suppose the road is not banked or the road surface is not kept inclined with the horizontal, that is called as the normal horizontal curve. In the villages, we observe this kind of curves, that is there is normal horizontal curve. In the case of the normal horizontal curve, I have drawn the diagram here. This is the vertical section of the vehicle. Therefore, we can't observe the circular track here. Here the circular track is of this kind. C is the center of that circular track. Consider the vehicle on this circular track. Now the vehicle, the forces acting on this vehicle. Number one, the weight of the vehicle. Number one, the weight of the vehicle. Now always the weight is directed, that is vertically downward direction. It is in the vertically downward direction, that is the weight. The second force, that is the normal reaction, is in the vertically upward direction. From the diagram you can see that these two forces get balanced each other, but the force of friction between the rubber tires and the road surface is along the curve, that is shown by Fs. This is the force of static friction, Fs. Now this force of static friction, the it supplies the necessary centripetal force. The formula of the centripetal force, that is equal to mr omega square or mv square upon r. That is in this case the centripetal force supplies the necessary centripetal force is supplied by the force of friction, and therefore Fs is equal to mr omega square. This is equal to mv square upon r. Now according to the diagram, the weight get balanced by the normal reaction, and therefore this normal reaction n is equal to mg. Normal reaction n is equal to mg. Now dividing the equation number 1 by 2, equation number 1 by 2, we get Fs upon n. Fs upon n is equal to here r omega square upon g. In this case, this is equal to v square upon rg. In the 11th science, we have seen about the coefficient of static friction. Coefficient of static friction, that is mu s. It is the ratio of the limiting force of static friction to the normal reaction. Therefore, this Fs upon n is taken as mu s. Mu s is equal to Fs upon n. This is equal to, suppose if we consider the linear speed, then this is equal to v square upon rg. Now our derivation is for the most safe speed along the horizontal circular road. While going through the derivation, we got Vs is equal to Fs upon N is equal to V square upon Rg. We want the most speed, safe speed, and therefore from this formula V square is equal to mu S Rg. And therefore from this we get the maximum or most safe speed V is equal to square root of mu S Rg. Mu S Rg. This is the required formula for the safe speed at the normal horizontal curve. This is can be taken as V is equal to square root of mu Rg. Mu Rg. Now here, if we increase the force of friction, that is the coefficient of static friction, then we can increase the speed, but the friction is having the upper limit, and therefore the speed is also having the upper limit. This is the derivation for the speed limit or the most speed along the normal horizontal curve. This formula can also be used for the gramophone disc. Suppose the disc is rotating. This is the type of disc. In this case, the coin is kept at this point. Now the coin does not slip inward. That is, for that the maximum speed V is equal to square root of mu Rg, where R is called as the radius of the curve. We are taking this one is taken as the radius. V is called as the coefficient of friction. G is equal to acceleration due to gravity. From that we can determine the value of the speed limit or the most safe speed. Now this formula can also be converted into the angular velocity or the angular speed, as we know that V is equal to R omega. V is equal to R omega. From this we can take omega there. The formula comes out to be equal to mu is equal to square root of mu G upon R. This is the formula for the most safe angular speed. Omega is equal to square root of mu G upon R. Now suppose if we want the frequency as mu is equal to as omega is equal to 2 pi m, therefore this formula can also be taken as n is equal to 1 upon 2 pi root of mu G upon R. Now this is the first derivation, that is the most safe speed along a horizontal circular curve or circular track or circular road. V is equal to square root of mu Rg. That can be converted into omega, that can be converted into the n, that is the frequency, number of revolutions completed in 1 second. That is the first derivation. Now the question in the book is that why are the roads are banked? That is the question. The question is why are curved roads are banked? That is the question in our book. That is, in the case of the road surface is kept tilted, that is inclined with the horizontal. That is the second diagram. This is the first diagram. Here at the turn, this is the turn. The road is kept tilted with the horizontal. The angle of inclination is called as the angle of banking. This type of roads you can observe on the highways. On the highways at the turn, you can observe that the road is banked. That is the outer edge of the road. Edge means curve. Outer edge of the road is higher level than the inner edge. The angle of banking, that is the angle made by the road surface with the horizontal, is called as the angle of banking. Here theta is called as the angle of banking. In this case, the weight of the vehicle get balanced by the normal reaction, but in this case, the forces acting on the vehicle, that is number one, weight mg. Weight mg always vertically downward direction. Weight is always in the vertically downward direction. Second force, that is the normal reaction n. Normal reaction n, this one is n, this is mg. The normal reaction n perpendicular to the road surface. These are the two forces acting on the vehicle. Now the n, that is the normal reaction n, are having the two components. That is, this is the angle of banking, this is again theta. It is having the two components. The component near the angle is called as the cos. The component in front of this angle is called as sine. Therefore, this component is n cos theta. This component is n sine theta. Now, in this case, you will observe that this n cos theta get balanced by the weight mg. N cos theta get balanced by the weight mg, but the component n sine theta does not get balanced, or it is the unbalanced force. It is directed along the radius and towards the center of the road. Therefore, this component supplies the necessary centripetal force. And therefore, n sine theta, the centripetal force formula is mv square upon r, or mr omega square. Therefore, in this case, this is the first case, horizontal road. This is the second case, on the banked road. There will be again third case. In the second case, we are not considering the force of friction. In this case, only the angle of banking. Due to the angle of banking, we are going to get the centripetal force. That is, we can drive the vehicle with the higher speed. In this case, here we have not taken the consideration of the friction. There will be the third derivation in which we are going to consider about the friction and the angle of banking. Now here the components n cos theta and n sin theta. The component n cos theta get balanced by the weight mg. The component n sin theta is the unbalanced component which acts as the centripetal force, and therefore n sin theta acts as the centripetal force, that is mv square upon r, and n cos theta get balanced by weight mg. N cos theta is equal to mg. This is equation number 1. This is equation number 2. Now dividing 1 by 2. In this case, dividing 1 by 2, we get here on the left hand side tan theta. Tan theta is equal to v square upon rg. Tan theta is equal to v square upon rg. Therefore, from this equation, theta is equal to tan inverse of v square upon rg. V square upon rg. This is called as the derivation of the angle of banking. Theta is equal to tan inverse of v square upon rg. V is called as the speed of the vehicle. R is called as the radius of the curve. Theta is equal to tan inverse of v square upon rg. If we want the most safe speed, that is, we want v. For the v, from this equation, v square is equal to rg tan theta. Rg tan theta. And therefore, the most safe speed v is equal to square root of rg tan theta. Rg tan theta. This is the most safe speed along the banked road. This shape speed depends on the radius of the curve. Second, the angle of banking. This speed limit can be increased by increasing the radius, that is the V is directly proportional to root R. V is directly proportional to the square root of tan theta. This speed limit can be increased by increasing the radius of the curve, but by increasing the angle of inclination, but there are the limits for the radius of the curve and the angle of inclinations. The angle of inclination किंवा angle of banking, the equation shows that as there is no term in small m, that is the mass of the vehicle, this speed limit does not depend on the mass of the vehicle. Same is the case here. V is equal to square root of mu r j. The speed limit does not depend on the mass of the vehicle. It is same for the scooter or the bicycle. It is same for the truck or the car, because it does not depend on the mass of the vehicle, and that is speed limit on the banked road surface. These are the two derivations for the most safe speed along the horizontal curve. In the first derivation we get V is equal to square root of mu rg. From the diagram, the normal reaction M get balanced with the weight mg. Draw a neat diagram. I have given you the pages of the notes. You have to write the notes on your notebook. Then from that we can understand M get balanced the weight mg. The unbalanced component Fs, that is the force of static friction. This friction is between the rubber tires and the road surface. Now here the question is why the road surface is banked. Why the road surface is banked? Now the banking of roads depends on the force of friction. That is the horizontal circular road. The most safe speed depends on the force of friction, but this force of friction, that is the coefficient of static friction, is having the upper limit. It is having the limit, that is we can't increase the speed limit above certain limit. Also the friction changes from surface to surface. We observe the rough road, tar road, the force of friction is different, therefore the speed limits are different. Also in the rainy season, or when the oil from the vehicles falls on the road surface, the force of friction decreases. That is, we can't totally depend on the force of friction to get the sufficient centripetal force. For that reason, the roads are banked. The question is, why are the roads banked? According to this formula, V is equal to square root of mu r g. Here the speed limit depends on the coefficient of static friction, but it is having the upper limit. It can't be increased above certain limit. Also the road surface, that is the coefficient of static friction from different is are different for different surfaces. Also in the rainy season or oil from the vehicles falls on the road surface, the force of friction changes. Therefore we can't totally depend on the force of friction to get the centripetal force, and therefore the roads are banked. In the second case, in the banking of roads, here we get the centripetal force, that is n sin theta. This component supplies us the centripetal force, due to which we get the same circular motion along the curved road. The centripetal force n sin theta is equal to mv square upon r. From that we have derived the formula, that is theta is equal to tan inverse of v square upon rg. V is equal to square root of rg tan theta. This is the most safe speed. This is also called as the optimum speed. Now remember that in this derivation we are not considering the friction. In the first derivation, we have taken the friction. There is one more derivation. In that case, we are going to consider about the friction as well as the angle of banking. These are the derivations. Thank you.